My screen still moving. Am I still on the Zoom? Yeah.
And the screen is shared. Wonderful. Okay, so we're just past the hour, so we should get started. I am delighted to introduce our speaker today, Dr. Delilah Gates, who's giving our colloquium today. Delilah double majored in physics and mathematics at the University of Maryland before moving to Harvard for her PhD in physics, working with Andy Strominger. She then took a position at the Princeton Gravity Initiative as a Princeton Future Faculty Fellow before returning to Harvard for a Future Faculty Leader Fellowship at the CFA, while she's also a visiting scholar here at the BHI. So I think the jury is in. You're probably future faculty. So today, Delilah will be telling us about the morphology of relativistically broadened line emission, coming from around spinning black holes and the like. And I'm delighted for you all to hear this lovely talk. So Delilah, please take it away.
All right, thanks for having me. I've got to say it's nice to be back in the BHI to work, and it's also nice to speak to you all again at the Colloquium. I remember after my first black hole project that I published with Andy and some of the other group mates in grad school, I also gave a talk here, so it's a nice roundabout for me. And I guess I've been thinking about black holes ever since then. So thanks for having me. So today I'm going to tell you, like Daniel said, about this idea of measuring black hole spin through relativistically broadened line emission, that is single frequency emission. And I'm going to tell the story in a few parts that I have outlined here. And this is kind of the culmination of things I started thinking about in grad school that I've finally in the last year or so been able to put together with some of my colleagues while I was at Princeton, Alejandro, who's now a postdoc at Los Alamos, and then 2 students we had over the summer that helped us write some code that made this possible. So I don't have to tell the people here in this room that black holes are very interesting and ubiquitous objects in our universe. There's something like 10 to the 19 of them, 10 to the 11 supermassive black holes for each galaxy roughly, and within that about 10 to the 9 stellar mass black holes. And of course, there's this gap of intermediate black holes that we've yet to observe. But despite being the most compact objects that exist over a range of masses, the other parameter we believe to describe them is simply their spin. So they're relatively simple objects according to general relativity. And their spin goes from 0 to a maximum value, which is the mass squared in natural units. So each black hole has a set limit of how fast it's allowed to spin if we want to maintain the fact that it is in fact a black hole who has a horizon. And so there's a lot of excitement about observing black holes with things like LIGO and Virgo and Kagra in the gravitational wave front. That's mostly the stellar mass black holes when they're merging. Of course, we now have some supermassive black holes that we're able to see on horizon scales images thanks to the Event Horizon Telescope collaboration. And there's exciting work being done on next generations to that collaboration, as well as a space-based extension, Black Hole Explorer. But traditionally, the way black holes, both in the supermassive regime and the stellar regime, have had their spins measured has been with spectroscopy, because we haven't had the ability to resolve what they look like on horizon scales. But we have had the ability to have fine spectral resolution on our instruments and collect the light around that from the stuff around them, and then look at it with fine spectral resolution. So spectroscopy, and specifically X-ray reflection spectroscopy, takes advantage of the fact that we can benchmark the rest emission, the rest energy of emission from around the black hole using the atomic makeup of the material in the disk. For instance, they tend to have a lot of iron, which has, for instance, a very loud line at 6.4 keV. So the idea is the accretion disk that surrounds the black hole gets irradiated by the corona, and then it re-emits light at those characteristic frequencies for the materials in the disk. And of course, we, far away from the black hole, collect that light, but that light is not at the rest frequencies. It's been shifted, of course, due to Doppler shifting. The stuff around the black hole is moving, as well as gravitational redshift shift. The stuff closer to the black hole will be more redshifted than the stuff further away from the black hole, or rather the light from the stuff closer will be redshifted more than the light from the stuff a little bit further out. And in this regime of observing black holes in X-rays, people tend to observe black holes in the regime where they're surrounded by radiatively efficient disks that can flatten out. And so the belief is that it's well described, the environment of the black hole, as having the stuff swirling around the black hole in the equatorial plane on stable circular orbits. Now, this gives us a handle at why this method might be related to observing the spin of the black hole. Because if we look at the geometry of the spacetime around the black hole, we notice that for the Kerr black holes, the innermost stable circular orbit is its radius away from the black hole is dependent on how fast the black hole is rotating. This innermost stable circular orbit, or ISCO, when the black hole is non-spinning, does not touch the horizon. And as we spin up the black hole, it gets closer and closer until at maximal spin, it kisses the horizon. And so people collect data and then they simulate emission. So here they've subtracted off some of the thermal continuum. And now you can nicely see in this observation, which is from Parker et al., that was showcased in Parker et al. In 2014. You can nicely see pulled out here, the iron line is very loud. And then you can simulate it with tools like Redline, Rexel, Silver. These codes have a bunch of names where you can code in some ideas about the environment of the black hole as far as the atomic makeup, as well as the spin and inclination you're viewing at. And you can model, for instance, this is just the iron line itself, and this is modeling the iron lines on top of the whole continuum.
What's the big bump on the left?
I'm not sure. There are a lot of pieces. There's a thermal continuum. It might be that there's Compton hump as well. I don't remember which piece this is. I would have to look it up. But
anyway, so the iron line.
But this is the iron line here. This is the 6.4 keV iron line.
And we're supposed to, the fact that it's sort of.
Yeah, it's very loud.
That it kind of slopes off more gently to the left than the right. That's predicted.
Yeah.
From there.
Absolutely. Yeah. Absolutely. And this method has been applied to something like 75 black holes or so. So I think it's upwards of 25 for the stellar mass black holes and binaries, and something like upwards of 50, but not too far upwards of those two numbers for the supermassive black holes. So they have both supermassive black holes and stellar mass black holes that this method has been applied to. And fitting the shapes of these lines to data, people come up with spin constraints for black holes. These are supermassive black holes, note the units here. And I like this figure from Reynolds, though similar figures appear in several papers, but because of the coloring, it's easy to describe that here they have the ones that they're able to put an upper bound and a lower bound on in blue, and the ones that they can put a lower bound, but they cannot put an upper bound away from maximal in red. And I'll note that this method of looking to measure black hole spin tends to suggest that we have a lot of high spin black holes, but it is also the case that it's in a way because of the more extreme frequency shifting you get when the black hole is rapidly spinning. Even if your prior was uniform, you would, with this method, be more easily able to detect higher spin black holes. So I'll just put that caveat up there. Okay, so here's some example of some iron lines. 6.4 keV is the rest energy. We have two viewing inclinations, 30 degrees, where we're measuring degrees from the spin axis. So 0 would be looking down the spin axis. So on the right, I have 30 degrees. On the left, I have 85. And in the colors, I have my different spins of my black holes compared to maximum spin. And so in studying these lines that people produce with these codes, I started noticing some patterns. For instance, if we look at this high inclination case, we see that the bluest edge is almost but not completely monotonic. As we're increasing spin, it's mostly increasing where this edge, the bluest edge of the line profile is, but not quite. We also notice, for instance, in the lower inclination case, they all have the same right hand side for the bluest, but they all have these bites here that are coincident with each other. But as we change the spin, we change the location, of this light here, pushing it further to the red as we spin up the black hole. And so looking at these patterns of the kinks and edges, I was interested in trying to understand exactly what pattern is hidden and how we might be able to use it to tell us about the black hole and the accretion disk around it.
This is fitted line? Or-
Nope, these are just simulated lines. These aren't
Okay.
fitted to anything. Yeah. I think they're normalized so that the area under them is one. Yeah. But in actuality, your units would be the number of counts for photons you're getting, and you could wait longer to build up signal. So, and in fact, as I was describing these kinks and edges, that's what we're going to focus on today.
Oh, the y-axis?
The y-axis,
Yeah.
that's what I was saying is, they're just, it's just some random normalized units. In actuality, it would be the photon count. But since we're not comparing to a real simulation, a real observation, it's just arbitrary units. But I think they're normalized so the area under them is the same. All these lines. Okay. All right. So now that, okay, the color's not showing up so well, it's bluer here and redder here, and the disk is bluish here, and it gets lighter, and then redder over here. So what I have for you is an image of an accretion disk here. If we could resolve it, we have the horizon in black, there's a gap, and there's the ISCO. Here's the outer edge. And then I've, in addition to coloring it by redshift factor, I'm also drawing level sets of constant redshift factor. And then I'm lining up on this side. Now I've divided by the rest energy just so I can use redshift factor, the line profile. And again, colored so you can tell which parts of the disk give you which parts of this line. And so it's this guy now that we will be able to decode, and I'll show you exactly how the line profile tells you exactly about the disk. All right, so in principle, the way these are simulated, of course, is to look at each pixel on the disk. You ask, what is the amount of light I'm getting from that pixel? And you ask at what energy, and you make this as a histogram. That's what you do to build these lines. But in principle, there's an analytic equation that governs this. So here we have our total flux. We have integrating over energy. We're going to assume there's these are observed energies. We have our solid angle since we're observing, and we have the intensity at each pixel. We can write the intensity at each pixel as the redshift factor cubed times the specific intensity of the disk in the frame of the disk. And then in principle, we would be able to then collect everything that relates to G. G is related to ES just by dividing by the rest energy. And so E observed is equal to G times ES. And so in principle, this, if I could do all of the math and analytically untangle and invert my equations, this would be my iron line, but it's not something I can do. So it's a little harder than just looking at the analytic form of this equation. But we can still, by looking at this correspondence of constant redshift factors, think harder in a way that allows us to disentangle what's going on. Of course, each of these each point on the x-axis is a single redshift. So you can think about all the flux at a given value as the flux you get by integrating across one of the levels in the redshift factor level sets on the disk. And so it turns out the sharp features and all the structure of this line profile is really governed by the redshift factors topologically. And so the sharp features, the edges and these kinks, it turns out, come from local minima and maxima of the redshift factor on the image of the disk. If I look at my inner edge and I ask, what are its local maxima and minima? It has a single local minima, which I call minimum observable redshift because it corresponds to the reddest part of my line. And then it also has a value that is its maximum. And it's the maximum for the inner edge is a curve that goes across the whole disk like so. You can also ask about the same for the outer edge of the disk. The outer edge of the disk has a local minima here, and that, if you look at the whole disk, it builds out a level that looks like this. It also has a single local maximum, which has a level that builds out to look like this when you take it off of the inner edge. And then it turns out, if you now look at the interior of the disk, not the single edges, it has a single local maximum, which is here. And I call it maximum observable blue shift because it's the bluest part of my line. So what we learn is that all the features of this line profile can be thought of as being seeded by critical redshift factor values on the image of the disk, corresponding to local maxima and minima of the redshift factor on the disk image. We have the extent, we have kinks, but it turns out we have more than just that. We can also look at the behavior on either side of any of these critical redshift factors as well. If we have a discontinuity like we have here, the side, we know that if the left-hand side is higher, where we have the discontinuity, we know that's a local maximum. If it was vice versa, it would be a local minima. And for critical redshift factors where where the line profile is continuous, we can look at the relative slopes on either side. And it turns out for this, for instance, for this one, which is a local maximum, you're steeper to the left than you are to the right. And it would be vice versa if it was a local minimum. Yes.
If you push out your outer disk radius
Yes.
instead of 50 to
Yes.
infinity, those two kinks will be gone
Yes.
eventually?
Yeah. And you're projecting ahead. I'll show you that in a moment because that helped us classify all the possible cases of what these line profile could look like.
Can I ask a quick question?
Yes.
So I'm having trouble understanding the relation with the intensity in the profile.
Yes.
So why is the bluest point the highest intensity? Is that because the redshift factor is the highest?
It's a combination of the redshift factor being the highest and the function that governs how bright relative radii in the disk are. So there's some kind of and in fact, in this one, I've chosen it to fall off like r to the -3. So you get more emission from the inner parts of the disk than the outer part of the disk.
I see.
And so it's a competition between the value that this has as far as the redshift factor and the values you get at neighboring radii. So it just happens to be in this case that it's such that, and it typical choices that people model, it tends to be a case that will give you this highest blue edge.
Thanks.
Yep. Okay. And it also turns out we can also understand the nature of the function governing the line profile to be a piecewise function, and the behavior on each of the intervals between the critical values is controlled by, of course, what you choose for your emissivity function, but that is shared by all radii in the disk. And the reason for the change in their behavior here has to do with the change in the topology of the levels. So for instance, in this region A, we have curves that connect the inner edge of the disk, the inner edge of the disk. We use a cap for those. In this region B, we have lines that connect the inner edge and the outer edge. In fact, we have a pair of them. So we use pairs of vertical lines for those. In this region C, we have lines that connect the outer edge of the disk to itself. So we use cups for those. And in this region D, we have curves that are closed circles. So we use a symbol circle for those. And this is nice because it actually allowed us to build a shorthand for describing one of these line profiles based on reading reddest to bluest, the topology of the level sets. So cap, parallel line, up, up. And just given this, it's also nice that you can also read off what order your critical redshift factor values are based on the change that occurs between neighboring topologies. If you affect the bottom, you have to do with the inner edge. If you affect the top, you have to do with the outer edge. And if you correspond to removing a piece, you're a minimum. If you correspond to adding a piece, you're a maximum, a local maximum. So that's the order of the critical redshift factor values for between these three. And then, of course, we just have the minimum and the maximum on either side. So it also is a nice shorthand that let us, that we were able to develop. Okay, let's talk about all the possible configurations now that we know how we might describe one of these line profiles. What are all the options we can get? So the easiest way to describe this is to start with the idea of an infinitely large disk. Now I'm showing here, viewed from the pole, a disk on compactified screen radii. So this outer edge is infinity. And so I'm assuming my disk could go out to infinity and I'm an observer at infinity. In this case, of course, all your level set curves are simply concentric rings. And of course, you're reddest on the inner edge and you get bluer as you go out. And I'm using red to mark the, they're the same because the max and min is only a single value for the inner edge, but I'll describe the reddest and bluest from the inner edge on these plots with red and purple. And so you can, that's why maybe it's hard with the lighting here, but there's a dotted purple line on the inner edge. As soon as I tilt the disk a little bit, what I see is now my level sets change. I have, as I had before, the reddest point is a dot, and then then the level sets become caps, which connect the inner edge to itself. And they continue to do that until a certain radius, the bluest for the inner edge of the disk. And then all the lines outside of there become closed circles. And the bluest point is no longer at infinity, it's some finite radius. And it's just like on the example I showed you before, it's a single point. You may notice that there's this one curve that seems to go from infinity to infinity. That's g=1. I will consider that to be a closed curve because, of course, everything at infinity is g=1. So you can consider that curve as closing up either around that way or closing up like this. So that's one special curve. And we can describe each of these two situations with a configuration. The first one, everything was just circles. Now that we've tilted this slightly, that we have a region where we have caps and then we have circles. As we continue to tilt the disk, we see we drive this bluest point inward. As I tilt it more, I drive it inward. I'll note here, you see there's a deformation of the apparent image of my horizon. That's just because of my compactified coordinates. On a real image, the horizon is always convex, the one that does not tilt in on itself. I always forget which is which, I apologize. But what we find if we tilt the disk enough, eventually we can drive this point to the inner edge. And then all the lines in this on this disk are caps connecting the inner edge and the outer edge. Okay, so those are my three configurations. Now you might ask, what does this mean for their line profiles? So here are just kind of toy drawings that are simplified. Here are those disks that I showed you before, and the toy version of the line profiles and the real version of the line profiles. And you can see when the ones that have a transition in them have a sharp transition, they now have a kink. The ones that are only a single topology are smooth. Okay, and we use the infinitely large disk as a benchmark from which we can then start to think about real disk. We have to plop an outer edge of our disk. Our disks don't go out to infinity. So what's going to happen when we do this? Some of the lines that we have here in the infinitely large case can run into the outer edge and change topology. So for instance, this is an easy one to see. Since all of these curves are caps, if I plop an outer edge, some of these curves will run into my outer edge. And then instead of being caps, they'll get capitated at the top. And it turns out here, we can also, depending on where we put down our outer edge, we're also able to take some of these closed curves and cut them off. For instance, you could imagine here, if I cut this one off a little bit, I could get some that change from being closed circles to being cups. And so it turns out that these are kind of what our configurations will do. The case where we are in this region here is going to be a little more complicated. What happens in the middle? This one will always stay the same. We'll just chop off the edge of it. this one will always have a bite out of the middle. So here's just an example of that for the type 1 and 3. You can see you get a bite taken out, and this one you just lop off the edge of it. In the more complicated case is the type 2 disc. You have two options. You can put your outer edge of your disc far enough out that you will leave the FFP on the disc, and in which case there are 5 options depending on exactly where you put your outer edge, where you will get you will change your topology and thus the shape of your line profile. And you can see that you can, if you're careful with where you put your outer edge, you can line up, for instance, the bluest from your inner edge of your disc and say the bluest or reddest from the outer edge of your disc. That corresponds to these 2 edge cases here. Okay. And then the final one is you can also, for these ones, put the inner edge of the disc so far in that you remove that finite flux point. And these ones actually no longer have a sharp edge in the line profile. But these ones are actually kind of rare because they would have to be really short discs. So this one is a little more reasonable. Okay. If you're curious, this also does work in flat space if you don't have GR and just have Newtonian mechanics. And here's non-relativistic and relativistic. This is what some people may have seen before, the double horn potential. And here I have this dotted line for what happens if you fill it up by taking the disk out to infinity. And what's interesting is this one always resembles actually type 3, where the bluest and reddest point come from the inner edge of the disk. Okay, but this is the lay of the land. It turns out this is our full zoo. There are only 10 configurations, that is orders, in which these critical redshift factors from the inner and outer edge of the disk, as well as maybe that finite flux point on the interior of the disk can be. All of them will have the first 4, only some of them will have that point. The reddest side will always come from the inner edge of the disk, while the bluest side can come from any of these 3 options. And because of what I was telling you at the beginning, we can usually, when given one of these line profiles, we can say, does it have a sharp edge? Does it not have a sharp edge? How many bites does it have? What's the relative steepness on either sides of all the kinks? And so usually we can distinguish which line profile we're given. Because we can distinguish which redshift factors corresponding to kinks in the line profile are in what order, that means we can tell which edge of the disk they're from. And because of this, we can learn about the disk by given one of these line profiles in a way that allows us to constrain perhaps the spin and inclination of the disk. So that's what we'll come to now. Yes.
I have a couple of
Yes.
clarifying questions.
Yes.
One is, so for the emission, you're assuming that the disk is emitting monochromatically, is that right?
Yes.
Okay, and do you think this would change if you added some I don't know, some distribution of frequencies that you're emitting at this whole story, or not much?
Okay. This applies to every single frequency in the disk. So if you integrate up over several frequencies, the story is the same for each frequency. The question that I don't know the answer to is, once you integrate up over several frequencies, you can imagine the bites from one frequency being here, the one from the next frequency being slightly shifted, and them shifting. I don't know if they add in such a way that you wash out all the kinks.
Okay.
But in principle, this applies to every single frequency in the disk, the same. Now, the shape from each frequency can be slightly different if the specific intensity is not achromatic, excuse me. But the fact that you get these bites and the locations of the bites, or what seeds the bites for each frequency is the same. The question is, do they wash out if you add them all up? They might. Okay, let's talk about the more interesting part, perhaps. I had fun mapping out this cute little mathematical story, but perhaps the more useful thing is, what can this do for us as far as spin measurements? Okay, so if we assume that the inner edge is the ISCO, as is often the case, or is often the assumption made in these measurements, then the reddest part of the disk, we know, always comes from the inner edge of the disk. And so we can map out as a function of spin and inclination that the values we get for that in the cases, in all cases, the bluest frequency that you get from the inner edge of the disk is one of the interior kinks on your line profile. And so we can also map the value that that takes as a function of spin and inclination. And so if you can imagine, if you can identify these two values, you can lay these over one another, and that gives you a handle on spin and inclination. Additionally, it's helpful if you're in the case where you have that sharp edge, that fifth critical value, the finite flux point. And so below this dotted line is the region where such a point would exist on your disk, assuming it's sufficiently large. Here we've said the radius at which it comes from. Of course, it gets, like we said, it gets pushed out as we decline our disk. And so we can also map out that value. And what we notice is the levels of this are relatively straight, are close to straight lines. They're not perfectly straight lines, but this means that the location of that sharp feature is mostly telling us about inclination. So that gives us a really nice handle on inclination. But you could say, Delilah, I don't know that the inner edge of my disk is necessarily ISCO. So let me tell you how we might get there, but let me take a couple steps towards it. So the first thing is, I told you that the maximum observable blue shift and red shift are the edges of my line profile. And a nice thing about those is I don't need to actually resolve the locations of the sharp kinks to be able to get at least a lower bound on the bluest edge and a upper bound on the reddest edge. And so if we look at the case of the maximally extended disk, what we notice is that the values for the reddest edge of the disk and the bluest edge of the disk behave differently, and they're one-to-one with spin and inclination. So that's very helpful. But of course, real-world disks aren't necessarily maximally extended. But the case for the maximally extended disks do give me bounds on what I could have if my disk doesn't go out to infinity or doesn't go all the way down to the ISCO. Because those give me the disk the broadest, so those give me the most extreme frequency shifts I could possibly have. Okay. And so in the case that we don't know the disk is maximally extended, what you can do is you can look at a line profile. You can ask about its inner and outer edges. So here I have in this one, I have 4 different line profiles with 2 different values for the inner edge, either the ISCO or 1.3 times the ISCO, and the outer edge either 40M or 7M. 7M is really contrived, it's quite short, but it's to make a point. And what we find is if we grab the MOB and the MOR, the maximum observable blue shift and maximum observable red shift, what we can do is we can make quadrants looking at the values for the maximally extended disk compared to my actual line profile. For instance, this very short disk has pink and light blue. Those lines are here and here. And what this does is it constrains my spin and inclination to be in this region. That's the union of A, B, C, and D. For any pair of them, these are 4 examples which have these 2 values or these 2 values. And if the disk does have, in this case, my finite flux point, then I would actually, in fact, be able to grab by the edge where these 2 cross precisely the true value. If it's not, I widen it a bit, but it still lies in this upper quadrant for in the spin and inclination plane of what the spin and inclination possibility combos could be. And this is similarly a case for if my disk is tilted and I don't have the possibility of having a finite flux point. We see that the true value is here. This disk here, because the inner edge and the outer edge, the bluest and reddest come from the inner edge, in this disk it's type 3. If it goes all the way down to the ISCO, like this one that extends from blue to red, the true value lies at their intersection. This one that's pink and light blue, the ISCO has been pulled away, so I move away from the true value, but I still know it's having some cutoff of the value of the line profile that I can observe. How close to zero does it have to be for me to observe it? And so here I've just normalized all of these by the peak value of the line profile, and then I've given two cutoffs relative to that.
And then,
Yes.
so the more is the left edge of the line, right?
Yes.
So do you have an analytic expression around that point? Can you tell how the intensity will vary, starting from zero at the more? Does it go up linearly, or is it quadratic, square root? How does it go?
I don't have it as a function. For this example that I'm showing here on the next slide, I've plotted it, but I don't have generically the form. I think it must depend.
It'll depend on your assumed I0 of R, yeah, right.
It'll assume on your, and your emissivity as well.
Yeah, the emissivity is what I was thinking of.
Yeah, excuse me, I said it. Yes, emissivity, it'll depend on the emissivity. I think it would be interesting to figure out if the emissivity, right, if the emissivity goes like R to the minus Q, can we say what this fall off is like? I haven't tried it yet, but that's.
Because that would be helpful, even if noise is cutting off the edge.
Yes.
If you can extrapolate,
Yes.
that might.
Usually what people do to fit these lines, of course, right? You can only see part of it and they're fitting it and they're assuming some kind of profile, whether it be a power law like R to the minus Q, or a lamppost where they have a corona above the on the spin axis that's irradiating the disk, and the fall off is set by the distance of the lamppost at a height h to the disk. So yes, absolutely. Okay, so when we can't observe all the way down to zero flux, which is the truth because we exist in a noisy world, despite the complaints of us theorists. What we see is this cuts off. If we're just purely looking to the extent, not looking yet to extrapolate, you can ask what's the best we can do with the directly observable portion of the line above our noise threshold. And so, for instance, if you have one of the type 2 flux lines that includes that extra point on the disk, that finite flux point, it doesn't affect the blue side. The apparent, what I call the apparent MOM, the amount of that would be above the noise is the same as the actual MOM. But for the red side, the apparent more gets pushed in as we look for the intersection of our noise floor with our line profile. And so similarly, to not knowing our disk goes all the way down to the ISCO, or it doesn't go out far enough that we capture the finite flux point where we could ask, well, how bad does this do for us as far as being able to constrain spin and inclination in the spin and inclination plane? Similarly, we can see here, we know we have this sharp side of the line, so we know the true value is going to lie along here. And if we could get the actual more, we would be spot on. But as we move our noise floor away, we are just able to constrain to this upper quadrant. And similarly, in this case, this is a case where we don't have that sharp line profile. In fact, these are the same line profiles that were shown in black on the previous page. They're just on a log scale now. And so this one is now a type 3 line, so it's not a sharp cutoff, but it still falls off sufficiently fast that this is approximately the same, but this guy is the side that changes. And so we see that there's our spot on value, but as we move our noise floor up, we open up the region to which we can directly constrain the spin and inclination combination. Yes.
You answered correctly, like essentially the height, like the bias towards measuring larger spins is coming essentially from the fact that the more is smaller. It can be smaller because for higher spins.
Because you can, the more always comes from the inner edge of the disk. As the black hole spins faster, the inner edge of the disk can come in closer. So you can get more redshift. Correct. That's usually what people are thinking about, is giving most of the constraining power for spin.
So if you have some flux observability floor, you're just going to measure. You have a chance to measure smaller spins.
Yeah. Oh, more extreme spins. Higher spins.
Okay.
The other way. It's possible to be more extreme. If you have a floor, you say this is what I see. The truth could be more extreme.
Yeah.
So it could be higher spin,
Right.
could be higher spin. This is spin this way, so it could be higher than what but I can put a kind of a minimum.
So all of those red points in that figure you showed, objects for which you only have a lower limit on spin and there's no upper limit,
Yes.
they are like this. You're saying that the observed line above the noise gives you a certain edge, and that gives you a certain spin. That's your lower limit.
Yes, but I wouldn't say that they're directly just looking at this analysis. They really are trying to fit lines.
I know, but now
But
with the
yes.
theorist hat,
Yes,
trying to interpret.
I suspect that's what's happening with there. But I mean, because they're also looking at specific models, it could be something slightly more complicated there, but that is my first principles theorist idea of what's going on.
Okay,
Yes.
okay, very good.
Yes. All right, as you were asking, Ramesh, oh, okay, I'll come to it this next part, but, so we were talking about the emissivity and this noise floor, because we're sensitive to exactly the way the line profile is falling off. I haven't really said anything about the emissivity. I've been assuming throughout this talk that it is just a fall off of r to the -3. This is a nice toy model. But you might ask exactly what does the emissivity control in this story? So also going to Laurent's point, if we still using just a single power law, r to the -q, we can look at fixing our spin and inclination and say what happens to my line profile as I change my emissivity. And what we see happens is the edges and the kinks stay in position which is part of why we were so interested in them, because they're in a way robust. But what changes now is the emissivity, is the behavior of the line profile between those critical redshift factors. What doesn't change is which sides are steeper still. It doesn't change that we'd be higher on this side than this side if it's truly a discontinuity. But what does change is the shape of the fall off. And to Laurent's point here's an example in the red one where actually this is not the highest. It's a little taller here than it is here because of the emissivity function fall off and their competition with the redshift factor from that bluest point. And so here I've just done it for the case of the line profile that has that finite flux point. So it has that extra line, and here's just, again, that type 3 where both the bluest and reddest points of the whole line are coming from the inner edge of the disk. But, okay, now you can ask, to Ramesh's point, how does the apparent mob and more change as we change the flux floor? Exactly what is the rate of this fall off? So I don't have it analytically, but at least I have this plot for each of these lines. I have the corresponding fall off where I'm looking in dashed dotted lines, the difference between the apparent more and the more. And you can, and as well as the mob and the apparent mob. In this one, because it is the case where we really do have this sharp edge, this difference is always 0, so it doesn't appear here. For this one, it does appear, but it turns out it's much lower than the fall off, than the difference on the red side as we change our flux floor, because it's a much steeper fall off, as you can see just by eye. And so these, okay, the coloring is hard because of the screen, but I have the value here for the purple lines crossing. This was one of the values I showed you on the last plot, and for the flux floor of 0.05, and this is the flux floor of 0.03 that I showed you on the previous plot, and this black line corresponds to the line profiles I showed you. So yeah, you can see that really this is usually like a couple orders of magnitude lower than the fall off here. And I terminated these lines once they hit past a local max. But yeah, so it could be interesting to characterize exactly what this shape is.
The actual power and how far it is valid, clearly it's not a single slope, right? That could be helpful. I mean, if noise is low enough, that you're in this asymptotic
Yeah.
region, then
Yeah.
you could extrapolate.
Okay. I'll also mention, we haven't talked much about the outer edge of the disk so much. We've mostly been talking about the inner edge of the disk and that finite flux point for giving us spin and inclination. But we do, given a line profile, as I described earlier, know which kinks correspond to the outer edge. So it also gives us a hope of measuring the outer edge of the disk. And it turns out there's a nice, when the outer radius is is large, there's a nice analytic approximation that you can make. And so you can, if you view a certain redshift factor for the kinks corresponding to the outer edge of the disk, you can also put a constraint on how large your disk is. And to your point, you asked about it going off to infinity. We use this as a nice bookmark for helping us organize our line profile description. But you can also think if your resolution is, you have to think about the fact that your observation has spectral resolution bins. And you might observe something that looks like it doesn't have any kinks for the outer edge. That would just mean it's so large that the values for the reddest and bluest of the outer edge of this fit in one bin. And that would, at least from the resolution of your disk, you say it looks like it's an infinitely large case, so it has, given my spectral resolution, my disk has to be at minimum this large. Okay, and then for the final piece, I'll tell you, this has all been under the guise of the standard disk model where everything is on stable circular orbits. And so you might ask, well, what if this is not exactly the case? As we start to move away from the standard model, how bad do things get? So we explored two different models. One is the Cunningham model, which is actually from the 1975 paper of Cunningham, where he first outlined fully relativistically how to calculate these spectra from observed disks. And in his model, you have outside the ISCO, particles still on stable circular orbits, but then interior to the ISCO, you let particles flow along geodesics towards the black hole while maintaining the conserved quantities of an orbiter at the ISCO. Now, of course, the emission is going to get more and more dilute as the material gets closer to the black hole. So the line emission should cut off eventually, but assuming we don't know where it's going to cut off, we could say, if it went all the way down to the hole, what's the worst that's going to happen to us? So the worst that's going to happen is if emission is allowed all the way down to the hole, of course, the reddest end goes all the way to 0. And then you can ask, what about the bluest part? Well, you can now, if you have particles flowing in this region interior to the ISCO, if you tilt your disk enough, the particles in this plunging region can be giving us the finite flux point, that sharpest blue point. They can be seeded from radii interior to the ISCO, and they can give us quite blue values.
So these are people that are coming towards us.
Yeah.
The fastest possible.
Yeah, so right, the disk has circular orbits and then it has stuff that's spiraling inward. It's spiraling inward and then it's kind of coming towards you. So it's the stuff that's spiraling still towards the black hole, but aimed towards you.
These calculations include the deflection of the ray and the fact that the horizon can obscure the other edge of the disk. All that is being included in these calculations.
Yes, this is only, and this is only, this whole story for everything I've said to you and for this is only including the obscuration, and it's only looking at the direct image of the disk.
Only the direct image. No.
Yeah.
Multiple orbits and all that stuff. Okay.
And so then if you compare to the standard disk where you don't have this plunging region, you can, of course, they match out here, so we don't have to worry about that. But for spin and inclinations in this region here, we have our standard values in dashed and our Cunningham values in solid. And what you see, it turns out, is that your Cunningham values are always more extreme than your standard disk values. So if the disk was Cunningham, when you assumed it was standard, you would systematically overestimate both the spin and inclination. And then the other model we looked at, maybe let's say we're not as pessimistic as we're gonna fill up the whole pudgy region, but we want to take into effect the fact that the disk interacts with itself. Things can't perfectly travel. It can't be emitting and have them perfectly ugly physics. So another model we looked at was still going down to the ISCO with emission, but now speeding up or slowing down the disk slightly by a factor of C compared to the Keplerian angular velocities. And what you see here, what happens is speeding up or slowing down the disk causes the location of the kinks to shift left and right slightly. As we speed the disk up, it turns out the ones that correspond to local maxima get slightly bluer, and the ones that correspond to local minima get slightly redder as we speed up the disk. And as we slow down the disk, the ones that correspond to maxima go a little less extreme, and so they get a little less blue, and the ones corresponding to the to minima also come inward, becoming a little less extreme. So there's also that caveat as well. I think this is one thing that's interesting to think about, because now it means we have a framework under which we can perturb our disk slightly and ask how much differences introduce into what I would infer for my spin and inclination, because usually these results are reported without any error associated with not knowing how well you are approximating the standard. Okay, and that's it. So just a summary, we started this talk by decoding these line profiles and talking about this topology of the level sets of the redshift factor. And for the standard disk model, we found there were 10 possible shapes we could get. And then we talked about how we can get spin constraints from the sharp features without having to worry too much about the emissivity. We did describe how it affects us when we talked about noise floors and things like this. And we also showed how the location of these sharp features degenerates as we change away from the standard disk model. And so there are new missions coming up, Axis and Prism, that maybe will be able to give us, especially Prism, higher resolution spectra. So it will be interesting, I think, to see whether this means we can be more clever about our spin constraints. Especially in the case that we could fit for the sharp features first, then the shape between the sharp features would give us information about the corona, and it would be nice to be able to try to fit those separately. So first, get a handle on spin and inclination, fix that, and then be able to change the emissivity function to try to back out the coronal geometry. And like I said just a moment ago, we now have a way we might be able to perturb our disk slightly to explore systematic uncertainties that come from the motion of the disk being slightly away from the standard model. And I'll lastly mention that this whole procedure I mentioned for looking at the topology of the disk and the sharp features in a line profile go beyond just this black hole model. It's a general procedure. If you have an emitting region on your sky, you can apply it to. So I know Don mentioned maybe like protoplanetary disks or something like this might be something fun to apply these methods to. Thanks.
Wonderful. Thank you, Delilah. Any other questions? Oh,
A very quick one, and beautiful, thank you. I was wondering whether you showed that in the case where the outer edge of the disk goes inwards, you go to transition from this sharp edge on the blue side to the upper edge.
Yes.
So I was wondering if this could be used to identify disks that have been somehow tidally truncated by a companion black hole, you know, to identify binary black holes.
That's a good question. I guess, let me clarify, are you asking about seeing seeing the transition happen?
No,
From
if
sharp
you
to-
if you see this, I mean, most of the time you see sharp edge. of
Yes,
it.
yes.
So if you see a soft edge, is that a strong indication that you have very compact disk?
No, it's more a sign that your disk is very inclined. Assuming
Yeah.
you trust the, this is 75, right? This is 60, 50, 30, 0. Yeah, this is 75. So it's mostly a hint that your disk is probably very inclined.
But it can also happen if you have, I think you showed that in the following slide or something. If you
Yes, right.
if you move the,
Yeah,
exactly,
these
yeah.
guys, right. Yeah, yeah, that's true, right.
Then you need
If you have something that could strip away the disk to make it very compact, yeah, this could also, seeing something like this would tell you, for some reason, you have a very compact disk, but these are really compact. This is like 6, this is like 12.5, maybe. I haven't looked at them and finding enough grain to know what, just how thin these have to be. But yeah, it's possible that this could be a sign that you get a way to look for truncated disks.
Yes, can we do one more? Oh, and then two. Peter?
So within the category of the stable or standard configurations, does that include all the different sort of morphologies of, or can it include them of optically thick, geometrically thick, optically thin, geometrically thin? I mean, there seem to be a huge number of models of this,
Yeah,
of the configuration. Would that cover that?
everything I've laid out here is for optically thick, geometrically thin. But like I said, I think you can apply this to any shape you want, and it would be interesting, for instance, I've heard people say that, you can have these thick discs and at certain angles, like, an outer portion of the disc along your line of sight can block part of the inner edge. So that might introduce an extra kink. So this could, or something like this. So this could be applied to other disc models, but I have no idea what it would look like. This is just the whole complete story for the optically thin, thick, geometrically thin. Thank you. As soon as I said I was, thank you very much. But the procedure should be able to be applied. So it's great. It would be great to find out if there are telltale signs, or if they mimic each other, or if they're very distinct.
Is there a question on Zoom?
Yes, question from Shep about retrograde spin. Do the breakpoints and regions in disk hold also for retrograde?
Yeah, so this, I haven't done it for retrograde, but this should, the story should, I believe, is exactly the same for retrograde. Yeah, I think exactly the same. I don't think, if the location of, for instance, if you're trying to correlate it to spin and inclination, for instance, the values you would get for these guys would be different, but the shapes you would get would be the same for the retrograde cases.
Actually, sorry, can I follow up on this? So the more redshift will be smaller than in Schwarzschild, because those were going out. For retrograde.
Yeah.
So that means
Yeah,
you're biased
the
to
more
maximum
extreme-
spin.
right.
You're biased to prograde maximum spin. Is that
Right, and you're biased to,
Like in the usual story.
yeah,
Okay.
right, okay, but also piggybacking off of that and the question that we just got. So the ISCO goes out as you spin up the black hole, so you should get in the retrograde case, the most extreme lines you'll get, the most broad lines you'll get will be from the lesser spinning black holes, I think. Because they have their ISCO closer.
Yeah, exactly. Okay.
Another one from Priya. What about sub-parsec binary black holes?
Sorry,
What about sub-PC binary black holes?
sub-PC?
I think parsec.
very close in binary black holes. So you have two accretion disks that are very close by. And might you be able to see something very interesting there?
Yeah. Again, like the answer to Peter on different geometries, I think you would get something different there. And I can't predict, you might get more than one interior point on the disk that's a local maxima, for instance, on the combination of their two disks or their shared disks. So, but you should be able to apply the procedure, but my guess is, yeah, you could get probably more interesting lines in certain cases for close close and distance paired binary. Yeah, I would
Thank
say.
you. Yeah, thanks.
Great. There are no more burning questions. We are just past the hour, so let us think. Go ahead again.
Let's talk.